Hey everybody, welcome to this week's FE exam review session for the electrical and computer section. Tonight we're going to be going over energy, work, and power. So essentially just a lot of fundamental mathematics and physics on energy, work, and, well, power. So we're going to go over the first problem right now. A bullet of mass 100 grams is fired at a wooden block resting on a frictionless horizontal surface as shown. A spring with a spring coefficient of 53 kilonewtons per centimeter resists the motion of the block. The maximum displacement of the block produced by the impact of the bullet is 3.4 centimeters. There are no losses at impact, and the spring has no mass. Most nearly, the velocity of the bullet at impact is. So now we got to figure out what the velocity of the bullet was before it hit the block. So the way we're going to do that is there's kinetic energy coming from the bullet, but there's potential spring energy from the spring. If we're going to figure out the velocity, we're going to need to figure out mass. We're going to need to figure out the crucial variables: mass, velocity, spring stiffness, and the spring displacement. Let's go back to our handy dandy camera here. So I did some of the work already, but I'm going to hold it up here just for you to look at. So kinetic energy and potential energy are going to have to equal each other because via the law of conservation of energy, it can't be changed or destroyed. It can only be conserved. That's why they're equal. So likewise, you got to find velocity. Oh, almost forgot. When you're plugging in the variables, generally, and as I recall on principle via my previous physics professors, and hopefully your physics professors have also taught you this or suggested this, is keep your units in newtons, meters, and kilograms, because that's fundamentally the units that we've been taught to use. So when you solve for velocity algebraically, you're supposed to get 247.52 meters per second. But if you recall back in the ABCD choices, you're given kilometers per hour. So likewise, you got to do a unit conversion. And like so, you're going to get 891 kilometers per hour. So let's go back to the choices here. That's about D. Option D. And if you guys have been following up on our FE exam workshops, generally our exact answers are not going to exactly line up with the options we're given with us, so it's better to estimate. So the answer for number 1 is option D. Number 2, a 0.05 kilogram mass attached to a spring is accelerated to a velocity of 0.4 meters per second over a distance of 0.1 meters. The spring constant is half a newton per meter. The spring's mass is negligible. Now we got to figure out what the total energy of the mass is. So essentially how this works is there's potential energy coming from the spring, like you pull it back against the spring and then you let it go. There's kinetic energy. So now you got to figure out what's the total energy in that instance, kinetic and potential. So this is where the math is just a little bit more straightforward. You just add the total energy up, and then you crunch in your variables. You're going to end up getting 0.0065 joules, 6.5 millijoules. Okay, so that one was a little bit of an easy example. Let's move on to number 3. In the mass spring system shown, the mass is displaced 0.09 meters to the right of the equilibrium position and then restored. What is most nearly the maximum position maximum velocity of the mass. Okay, let's look back at number 3 here. Look at the work I did. So basically what happens is if you move the mass to the right a little bit, 0.09, then likewise the left spring is also going to be moving 0.09 meters. They're both working in tandem with one another to balance out that block. And coincidentally, the spring stiffnesses of both springs are the same. So what you have to do is, similarly to example 1, you got to equal the two potential energies from the springs to equal the kinetic energy. But since K1 and K2 are the same, I just left it as kx squared. That's simple. And likewise, plug in your variables, figure out what velocity is. So we're going to get 13.5 meters per second. So if you go back to our choices here, that's about D. Oh, almost forgot. For number 2, it's option C for the 0.0065 joules. I don't know why I forgot that earlier. Anywho, moving on to number 4. The 85 kilogram mass shown is guided by a frictionless rail. The spring is compressed sufficiently and released such that the mass barely reaches point B. The spring constant is 1500 newtons per meter. Once again, so basically you compress a block, you let it go, there's potential energy coming from the spring and kinetic energy coming from the block. But then that's going to both have to excuse me. So that's going to have to equal the gravitational potential energy of point B. So we have this equation right here. mgh plus the kinetic energy is going to equal mg times h plus 1. And then when you use the distributive property, the mgh's are going to cancel. And since we're just finding velocity, that actually makes this a lot easier. So at the step where it says half v squared is equal to g, times everything by 2, and then square root it, you're going to get something like 4 point something for velocity. That's going to be option B for problem number 4. Now let's move on to the next 8. Number 5, the 170 kilogram mass shown is guided by a frictionless rail. The spring is compressed sufficiently and released such that the mass barely reaches point B. What is most nearly the kinetic energy of the mass at point A? Okay, so it's essentially the same problem, the same premise, and more likely going to be the same equation. So if you look at the work I did for number 5 here, yep, same equation. But since we were looking for the kinetic energy here, we don't need to do any work. So as I've mentioned previously, the mgh's are going to cancel, likewise in number 4. And then all you need to do is just plug in mg, the mass and gravity, just to get the potential energy at that point, which is 1,670 joules. Ah, 1,670. Okay, I don't know what's wrong with me. Anywho, so if you go back to the choices you have for problem 5, you're just going to get option D when you round it up. Next up, problem 6. It's going to be the same equation as before, except you're taking into account the potential energy of the spring and the gravitational potential energy. The 40 kilogram mass shown is guided by a frictionless rail. The spring coefficient is 3,000. The spring is compressed sufficiently and released such that the mass barely reaches point A. What is most nearly the initial spring compression. So as I mentioned before, you're just taking into account spring and gravitational potential energy equaling each other. And all you need to do is just algebraically solve for x, which when you get down to it is just going to be 1.35 meters. Or if you look back in the option C, 1.4 meters. Number 7. A 1,500 kilogram car traveled at 100 kilometers per hour is towing a 250 kilogram trailer. The coefficient of friction between the tires and the road is 0.8 for both the car and the trailer. Approximately what energy is dissipated by the brakes if the car and trailer are braked to a complete stop? Okay, so fundamentally when you think about this, the energy... Okay, so you're driving your car, right? And it's got a certain kinetic energy to it. Now, it's going to take equally amount... To get it to go to a complete stop, it's going to take equally as much kinetic energy to stop the car. So, actually, we don't even need the coefficient of friction. You just need to figure out the kinetic energy. But fundamentally, this is just a car and a trailer attached together. So, those two masses are going to add up. And if you look at the work I did, 100 kilometers per hour is, well, you know the drill. Just do a unit conversion. You're supposed to get 27.78 meters per second. And then bing, bang, boom, plug it into your kinetic energy formula, and then you're going to get 675 kilojoules. Which, if you look back at the answer, is supposed to be roughly 680 kilojoules. Option D for number 7. Next, number 8. And this looks like we're getting into the problems where they start to feel like a doozy. Number 8. A 12 kilogram aluminum box is dropped from rest onto a large wooden beam. The box travels 0.2 meters before contacting the beam. So you drop it onto a beam and then it's going to, compress the beam a little bit. But then after the impact, the box is going to bounce up 0.05 meters above the beam surface. Approximately what impulse does the beam impact on the box? So essentially you've got two different displacements going on here. Essentially, when you drop the beam onto the box, it's going to be gravitational potential energy downwards onto the beam by 0.2 meters. But then when it's released back up, it's 0.05 meters. And it mentioned in the problem there's a certain impulse. Impulse, by definition, is essentially a change in momentum. So what we need to do first for number 8 is, after you have your variables plugged in here, you're taking into consideration two different cases of gravitational potential energy equaling kinetic energy. But of course the values are going to be different because the height is. So if you plug it in for case 1, that means when the box drops onto the beam, it's going to be 1.98 meters. But when it's going up 0.05 meters, that's just 0.99 meters per second. Now, for the impulse, and you definitely want to be careful about this, and fundamentally in physics, I hope your professors or teachers taught you something about, like, perspective. Like, what would you consider up or down? So, when you drop the box onto the beam, it's going down, but when the beam is going back up, when the box is going back up, that means it's going in the opposite direction. So you need to, because you're taking impulse into account, you're going to be doing 1.98 minus the negative of 0.99. So it's down, then up. So now it's going to turn into an addition. And then plug in your variables, you get 35.66 Newton seconds. which is about 36 newton seconds. That would be option C. Okay, moving right along. Two balls both have a mass of 8 kilograms and collide head-on. The velocity of each ball at the time of collision is 18 meters per second. The velocity of each ball decreases to 10 meters per second in the opposite directions after the collision. Approximately how much energy is lost in the collision? So this is simply a difference in energy, and since we only took into account mass and velocity in the problem, it's just a difference in kinetic energy. But the mass of the balls are the same. So if you look at the work right here, now there's a reason I put a 2 there, because the masses are the same. So the 2 and the 1/2 will cancel, and then it's just m times v2 squared minus v1 squared. Plug in your variables. The difference in kinetic energy is going to be almost 1.8 kilojoules. If you go back to your choices in number 9, that's option C. Yep, 1.8. All right, moving right along. Number 10, the impulse momentum principle is most useful for solving problems involving A, force, velocity, and time, B, force, acceleration, and time, C, velocity, acceleration, and time, D, force, velocity, and acceleration. Okay, we've got a conceptual problem here, so I'm going to need to show some of the work I did. Fundamentally, momentum is equal to mass times velocity. But remember, momentum and forces also have to be conserved. So if we take it into a differential perspective for force, it's ma, yes, but actually let me write that down. Okay. So that's essentially, so fundamentally, acceleration is the derivative of velocity, essentially. So therefore we get m dv dt right here. But if there's a change in velocity but the mass is conserved, then that would also mean a differentiation of momentum. But if you took this into a algebraic perspective, given these equations here, that would essentially be mass and velocity divided by time. Reason I put the t down here is because mass, fundamentally, acceleration is velocity divided by time. So acceleration isn't really taken into account here. So let's look at the problems again, the options again. A, force, velocity, and time. Well, that was directly in the derivation that I explained. B, force, acceleration, and time. No. Okay, so basically any option in number 10 here that has acceleration is a no-go, especially C. Okay. 2 more problems, guys. Hang in there. Number 11. A 50 kilogram cart rolls onto a frictionless surface at 40 meters per second. The cart is decelerated by a spring, initially at equilibrium with a spring constant of 20 kilonewtons per meter. Most nearly, what is the maximum deflection of the spring? Okay. So once again, kinetic energy is going to equal the spring potential energy of the spring. You know, half mv squared is going to equal half kx squared. So likewise, you have your variables here, plug it in, figure out what x is. And the displacement of the spring is 2 meters. Yep, 2 meters. Option D. Okay, last problem, everybody. A pickup truck is traveling forward at 25 meters per second. The bed is loaded with boxes whose coefficient of friction with the bed is 0.4. What is most nearly the shortest time that the truck can be brought to a stop such that the boxes do not shift? Okay. Now, if you remember in your classical mechanics physics class, the only way we're able to get a friction force is if we have the normal force. And when an object is sitting on a surface with gravitational force acting downwards, there's an equal and opposite normal force acting upwards. So the normal force is going to equal the weight. And then once you get the normal force, you times it by the coefficient of friction. So the only variables we were given were velocity, coefficient of friction, and gravity. So remember that fundamental problem we had in number 10 about, remember that conceptual problem we had in number 10 about what variables are going to apply to impulse? Well, here's where we need to apply that equation again. So impulse is going to equal the mass times the difference in velocity. But remember when I also talked about how momentum is essentially force times time, but the only force we're talking about here is frictional. So therefore, you get this second equation right here. From there, it just becomes pure algebra, where you have to substitute in equations to figure out what, and maybe do some cancellations along the way. So remember, the truck is being brought to a complete stop. That means the second velocity is 0. So it's 0 minus v1 for the numerator. And for the bottom equation, because this is a frictional force, which is acting the opposite direction, that's why we make it negative. So the negatives are going to cancel for the numerator and the denominator, thus for what we have here, but the masses will cancel. So now all you have is velocity, coefficient of friction, and gravity, just like we have right here. So now all you need to do is just plug in velocity, coefficient of friction, and gravity into time, and then you get 6.37 seconds. Which, if you look back at number 12, is option D, 6.4 seconds. Ooh, man, that problem really was a doozy. Anywho, for those of you who are watching this video right now and are looking to take the FE exam, if you're a electrical or computer engineering or computer science student, thank you for taking the time to watch this video. And I'm also working out a different form of how to instruct this material instead of just using the camera and writing down on the paper. Because I know the use of the camera initially was janky. But anywho, thank you guys for taking the time to look at these problems and then also work with me on them. I hope this knowledge has been helpful to you, and we will see you in the next week of the FE exam workshop. Hope you all are having a good night and staying safe and healthy amidst quarantine. Good night, everybody.